exponential term or exponential nature of the current will exist, and after some time that doesn't exist. What is that? And for what amount of time it will exist, and for what amount of time it will not exist, we shall see again. So now what is happening? One more reason why the current in the inductor is not changing instantaneously. We have already established the fact that in an inductor the current doesn't change instantaneously. Okay, it will change from this from this expression. Now I got to know that it will change exponentially. Okay. Now what happens when the switch is closed in the circuit? Now coming back to the circuit. When the switch is closed, when the K is closed, the current starts flowing in the inductor. Now inductor will create its own flux. It is the very nature of the inductance that when the current is carried by the inductor, it will create its own flux. Now this flux created will induce some self-induced EMF in its inductor itself. So this VL of t is nothing but my self-induced EMF. Now this self-induced EMF, by the nature, because anything that is induced electromagnetically has to oppose its own cause. So as per Lenz's law, the self-induced EMF will be opposing its cause. Now the cause for producing the self-induced EMF is the change in the value of current. Okay, so this self-induced EMF will be opposing its cause of its production, that is the change in the value of current. So there is a small note I would like to mention. In some textbooks it is, I don't know whether it is by mistake it has been given or it is a oversightness. It is mentioned that the self-induced EMF will oppose the flow of current, which is, I feel, a wrong statement. The self-induced EMF will not oppose the flow of current. The opposition for the flow of current is offered by the resistor. It is the duty of a resistor to oppose the flow of current. But whereas self-induced EMF will not oppose the flow of current, it will oppose the change in the value of current. So this VL of t, in some textbooks it is mentioned that it will oppose the flow of current. If that is the case, then the value of current should decrease. But this is not happening in inductor. Whereas in inductor, by its nature, it will oppose the change in the value of current. So because of this changing in the value of current, there is a self-induced EMF, and as per the Lenz's law, this self-induced EMF is now opposing the change in the value of current. Hence, current will not be able to reach its values instantaneously. So this current will not reach the steady state value V by R instantaneously. So it is exponentially increasing, and after some period of this exponential variation, it will reach its steady state value. So this we have to observe. So that itself, in the other words, with AC system, I call that current lags behind the voltage by some value. Okay, current lags behind voltage by some value. So this we have to observe. Now if I have to see how exactly the current is varying with respect to time. So let me plot. This is time t, and let this be I of t. Let this be I of t. Now the steady state value of the current is V by R. Now this is the steady state value of the current, V by R. Initially the current is 0, the initial condition is 0. Therefore I can say the current varies exponentially. The current varies exponentially. Okay, so the variation of the current is exponential. So this is the maximum value. The steady state value, or to be specific, purposely I have drawn this. with some gap between the maximum value and the curve. There is a reason for that. We shall see. Okay. So now let us consider the time constant of an inductor. See, for every energy storage device, there comes a time constant. Okay. So time constant is that the period or the span where there is major variation of the voltage or current in the element. Okay. So that time constant will give us the nature, okay, of the variation, either increasing or decreasing. Okay. So let tau be time constant, for inductor or for given circuit. And this tau I will be giving as L by R. L by R seconds. Tau I will be giving as L by R seconds. Okay. Why L by R seconds is, come back to the expression of the current here. Okay. So I am taking time constant. Okay. Here R by L I have multiplied with the time. So I will take time constant as L by R. Okay. So I want to make the exponent power to be a dimensionless quantity. Okay. To be a dimensionless quantity. So I will take the time constant as L by R, which is the reciprocal of R by L. Okay. So now what I will do, we will see how the variation of current is happening in the circuit at various time constants. Now I will go on putting the value of t. So let us know I of t for t equals to tau, 2 times tau, 4 times tau, and so on. Okay. So let us substitute the value of t with respect to tau here. So for t equals to tau, now I can write I of t is equals to V by R minus V by R e to the power minus R by L into tau is L by R into L by R, which is equals to now V by R minus V by R into e to the power minus 1. And 1 minus E inverse will come out to be 0.632 times V by R. 0.632 times V by R. So what I can mention on this plot is, for one time constant, the value of current rises for 0.632 times of the steady state value. I can say that in one time constant period, the current rises to 63.2% of the steady state value of the current. Okay. Now this is very clear an exponential variation. When I take integral multiples of time constant. Now let me see what happens for t equals to 2 times tau. Okay. So I of t is equals to V by R minus V by R e to the power. So if it is R by L into L by R, then it will be 2 times L by R. I will directly take it as e to the power minus 2. We'll take it as e to the power minus 2. So this is equals to, I think I have pre-calculated this, 0.864 V by R. So for the next time constant, here, so this is 1 tau, this is 2 tau. The current rose up to this value, and this is 0.864 V by R. When I further do this, for T is equals to 4 times tau. So I of T will be V by R minus V by R e to the power minus 4 equals to, it will be 0.997, sorry, 0.981 V by R. This I have pre-calculated on my sheet, okay, to save the time. Next, for T equals to, 6 times the tau, my I of T will be, I will write this as 0.997 V by R, directly I am writing. For T equals to 8 times tau, my I of T will be 0.9996 V by R. Now if I go on substituting for T equal to 10 tau, 12 tau, 13 tau, 14 tau, it will be 0.999 something, 0.999999 something, 0.999999 so on. So what does it mean? Okay, the steady state value of the current will reach at an instant where T is a large multiple of time constant tau. Okay, it means that the steady state value of the current is reached as T tends to infinity. You can observe. Now if I continue doing this and if I substitute T tending to infinite value, so I can write this as I of T is equals to V by R minus V by R into e to the power minus R by L into infinity. So what is e to the power minus infinity? Is 0. E to the power minus infinity, I can write it as 1 over e to the power infinity. E to the power infinity is infinity, 1 over infinity is 0. So my second term becomes 0. So this is equals to V by R. So when I say ideally, the steady state value of the current is reached at infinite time. But when I take practically, the steady state value of the current is reached after 6 to 8 time periods or time constants. Okay, so practically I can take 0.9996 as 1 or 0.9999 something as nearly equal to 1. So for my practical calculations, 6 to 8 time constant periods are sufficient for me to know the final value or the steady state value of the current, but whereas ideally the current reaches steady state value only at infinite time instant. This is one observation. The second observation what I can have with this analysis is, for the first time constant, for the period of first time constant, there is a large variation of the current exponentially from 0 to 63.2%. For the second time constant period, the variation is only nearly 20 or 22%. For the third time constant, the variation is hardly 86.4% to 98.1%. It is hardly 12%. Whereas for the next time period, the variation is 1%. 98% to 99%. So what does it mean is, the current varies, okay, largely exponentially. Obviously the current varies largely exponentially only during the first time instant. first time constant period. It varies during first time constant period. Whereas the variation gets slower, okay, the variation gets or decayed as the time increases. So this is the second observation. So from these characteristics, what I can observe is, from this plot, what I can observe is, first point, that ideally the steady state value of the current in an inductor is reached at infinite time. Second, during the first time constant, the variation is very large, whereas for the next time constants, the variations goes down and down. So these are the two observations what we can have. So next we shall see, this is how the current is varying in the circuit. Now what about the voltages? So there are voltages, there is voltage across resistor and there is voltage across inductor. Okay, so now we shall see the voltage across inductor and resistor. Voltage across R and L. Here I will split. Across resistor, VR of t is nothing but I of t into R of t. I of t into R. So substitute the value of I of t here. So I can write this as V by R minus V by R e to the power minus R by L into t multiplied by R. R will cancel out from each term. So VR of t equals to, I can write V minus V e to the power minus RL into t. Okay. So this is the voltage across resistor. Coming to voltage across inductor, VL of t is equals to L di of t by dt. L di of t by dt. Substitute I of t here. So VL of t is equals to L d by dt of V by R minus V by R into e to the power minus R over L into t. So when I take the differentiation of the bracket term, first term becomes 0, L into 0 minus V by R, it remains as it is. E to the power minus R over L by t will be e to the power minus R over L by t into minus R over L. So this will be, this R will cancel out, this L will cancel out. Okay, minus into minus, it will be plus. So V e to the power VL of t, it will be V into e to the power minus R over L into t. No doubt, both voltages are varying exponentially. Why? Because current is varying exponentially. Simple. Both voltages are because of current flowing in them. The nature of current will decide the nature of voltages. There is no doubt in that. But how the variation is? Observe, the variation of voltage across resistor is exactly like the variation of current. Okay? So it means the voltage across resistor is rising exponentially because current is rising exponentially. So we have established the fact that the voltage will always be in phase with the current for a resistor. Therefore, I can conclude from these two expressions that voltage across R increases exponentially. No, both are varying exponentially, but across R it is increasing increases exponentially. Whereas voltage across L, it is the negative power of exponent, so therefore it decreases exponentially. Voltage across L decreases exponentially. Now if I plot the same, let this be voltage, let this be the steady state value of the voltage or the maximum value of the voltage V, then the voltage across resistor increases exponentially. It will not touch V until infinite time. This is VR of t. Then voltage across inductor decreases exponentially. This is VL of t. The voltage across resistor will reach the steady state value or the maximum value V at t equal to infinite, which is the steady state voltage of resistor. Because at t equal to infinity, the current reaches the steady state value, which is V by R. Now the steady state value of inductor voltage is reached at t equal to infinity. So what is the steady state value of inductor voltage? It is 0. The steady state value of inductor voltage is 0 because under steady state the inductor is acting as a short circuit. So steady state value of voltage across inductor is 0, which is reached at t tending to infinity. Only at t tending to infinity in this expression VL of t becomes 0 ideally. Okay, but practically the voltage is so low that it can be considered to be 0 after 6 to 8 time constant periods. So these are the two observations that we should have for voltages here. So at t tending to infinity, VL becomes 0, VR becomes V. Because at t tending to infinity, inductor acts as short circuit. So therefore drop across inductor becomes 0. All the voltage that is applied to the circuit is now available across resistor. This is simple Ohm's law. Okay. So what all the facts we have established in the previous lectures about L are all the facts are getting justified with these expressions and plots. This is what is required in the study. So we should be able to appreciate and accept, okay, and understand and analyze all these things which the mathematical analysis is telling to us. Then only we will be getting a greater picture of the concept. Else what will happen? Majority of the times the students will try to remember or to practice these all contents in bits and pieces. The normal mistake what the students do is they consider the first topic as one independent topic, second topic as one independent topic, third as one independent topic. But it is not the same. Everything is related because all have come in the same module. It means everything is related. So what all we have discussed in the first few classes will be repeatedly justified through analysis in forthcoming classes. So that you should be in a position to understand, appreciate, analyze and apply. That is what the levels of learning are required. Okay, so with this, today we'll end the session. In next session, we shall see what is the analysis, okay, with a undriven circuit and how it is to be taken and how it is to be analyzed. Okay, so with this we'll end today's lecture. Thank you.